I realized never really done an introduction, I don't think. And I thought it might be helpful to give some context. So I'm going to start with just a little bit of background on myself, and I think it does inform. Like I was talking, I don't know if you've ever heard the phrase research is me search, that whatever you end up working on, it's a part of your personal journey.
Makes sense. All right.
Well, thank you all for coming. This is the final session in the series. I do have some work that I'm planning to continue past this out of both curiosity and to bring some of the things I'm exploring to a clear stopping point. But we're going to continue discussing multi-agent influence diagrams, which we've covered the past 3 sessions. And in those sessions, there were some teasers about how they connected to generalized dynamical systems and CAD CAD modeling. And in today's session, what I'm really hoping to accomplish is to lay out some frameworks that MAIDs have suggested to me that might be applicable or might be useful in the CAD CAD modeling process overall, which includes both communication and structuring, and the things, the specific CAD CAD structural things in terms of coding. And I have a roadmap. Of course, the map may not end up being the territory either prescriptively or descriptively, but this is the overview that I'm giving myself for today. And it's going to be a wide open session where I'm totally open to talk about anything that this suggests. So I'm going to be sure that we leave that time at the end. I realized I've never really done a biography or an introduction for this audience. And so some of you I've talked to in the past, and you have a very clear idea of where I'm coming from. But I do think that that individual perspective will give a little bit of additional context to some of the things that I say. So I think it's worth doing. Then, after that personal kind of review, I'd like to do a very brief, very high level review of MAIDs and what they are and the things that we've covered in the previous talks. Even if you haven't come to any of the previous talks in the series, I'm hoping to make this lucid enough that it will still be valuable to understand what MAIDs can do to inform GDSs and CAD CAD. But we can't have a lot of time to get bogged down in some of the granularity of different MAID structures. So some of these things will be like, see the previous talk, or let's discuss offline if it needs to go deeper. Part 2, then is going to be the meat of the discussion, which will be some CAD CAD frameworks and code structures that I've written with an eye towards using MAIDs concepts in specific experiments. The experiments themselves are still at the proof of concept stage and need a little bit more work before they're fleshed out, but we're well on our way and have good momentum. And the final thing is the future directions, both what I personally hope to complete as part of calling this project settled, and also what this may suggest in terms of. So that's an overview of what I see us doing today. So in my academic career, I did some research. Some of it is what would be called scholarship four-year model, which is more traditional research like published papers and computer code and things like that. But the institution where I worked was a regional comprehensive unit. So in addition to intellectual advancement in the broader sense of scholarship of discovery, there was also a large emphasis on serving the needs of the community. So one way that I did that was through undergraduate research advising. And it occurred to me just recently, I was actually doing something similar to what industrial organizations are doing, just in an academic setting, and that I was trying to build a consistently successful research project, research process. Now, this depended on the definition of success. It was twofold. The first was this was about student growth primarily. So whether it was they were looking for something that could lead to an internship that they could show, or they were looking to publish a journal article to be admitted into graduate school, every student was going to set a different interest. And this second thing, this was a combined math computer science department. So often students were starting with basically no background. Some of the students that we worked with were still in college algebra, so their mathematical maturity was virtually, it was in the very beginning stages, let's say it that way. But they had, what we could trust was that they had an introduction to CS course. So they had a lot of, there was a clear foundation of computing skills and knowledge. And you combine this with the fact that we're working in teams. Well, undergraduate students are very unpredictable. So in addition to needing to find good entry points, which may not presume a lot of background knowledge and getting people engaged, we also have to have very clear ability to do handoffs. I used to tell people, you need to code so that if you die next week, I can plug someone else and replace you. And this led to a lot of emphasis on structure. And some of this structure that I'm going to be talking about are things that I think would have fit well in that environment. Now, obviously, everyone at Block Science is much stronger than the type of audience that I'm talking about doing research with and that I built these processes on. But it's still, I think, good to see what the types of structure that can be built and how they might translate to this more mature environment. In a related vein, again, focused on student success as one of my primary metrics of success in my career, was building teams that engaged in undergraduate math competitions. Again, starting with no assumption on background. And I felt like this was definitely viewed as research under the Boyer model by my institution. Doesn't translate to published papers. But we had some tremendous successes. And so team building is something that I've always been interested in, and specifically how to leverage the strength of different individuals. And that leads to multi-agent influence diagrams. How? Well, first, one of the things that I don't think I've made explicit enough in the previous talks, but I'd really like to emphasize now, is that one of the things MAIDs do in our modeling process is leverage these interconnections between different types of thinking about a problem. So in my work, as you know, many years ago, I couldn't trust that students had strong symbolic. It was necessary to use many different representations. But that's actually a fundamental principle of math pedagogy, is that when communicating, the more different types of representations you can leverage, the more successful you ultimately be in creating deep understanding for a variety of audiences. And MAIDs are a great illustration of this, because MAIDs have a very clear diagrammatic structure. And that's one of the things that we've been able to leverage is the diagrammatic structure, not only for understanding the problem and understanding the models, but also by having this diagrammatic structure, it creates the opportunities for the types of algorithms and search techniques that we discussed in more technical detail previously. So it gives us something to look at. And this is something that's accessible as a building block, regardless of one's quote unquote mathematical maturity. This is the visual component, but it connects to strong symbolic components that we talked about previously in terms of things like algorithms for finding Nash equilibria that use this and computational techniques. Also verbal representations, right? There's a story that we've told about this, that Alice wants there to be a deck with no tree, and she may be willing to poison the tree to get it. And Bob wants there to be a tree, and if he notices the tree is sick, he may be willing to call the tree doctor to save it, or he may call the tree doctor just because he's a responsible tree owner. This connects the verbal description of the situation to a clear visual structure in a way that's really helpful. And then that also leads to the quantitative aspects that can be attached to this. Things like this is a probability distribution. So that's more technical and quantitative. And the goal is to tie all of these things together whether we view it as a building process towards a specific type of model, or whether we just view it as something where we're making connections with different audience members in different ways. The important thing that I think this emphasizes is how these embracing diverse representations can be very valuable overall in terms of communication and in problem solving. So the MAIDs kind of naturally suggest a framework of modeling. If you want to build a model of a scenario or process, whether that model is computational or mathematical or symbolic or however you're wanting to build it, in order to build a MAID, you have to ask specific questions, and you can ask those same specific questions about any situation. Like, who are the agents? What do they want? And what do they want depends on other information that's available to them or other things that happen. And then how do they measure how successfully they have gotten what they want? So this connects to the idea of utility functions, which are critical in terms of defining the agent in a MAID framework. And then what decisions do the agents make? In which order? And what information do they have when they make these decisions? These are the decision rules and strategies that agents have. And again, even if we're not building a MAID representation, if we want to think in terms of agents, utilities, and decisions, if we can pin down and ask these questions, it gives us an entry point model. And finally, what other processes occur? Might be viewed as natural processes or passive agents, where they're not making decisions. A tree doesn't according to the laws of nature that it follows. It's here another way of saying some of these things that really corresponds in the same way to these questions. What are the state variables that need to be tracked, and how are they organized? In a MAID, variables are belong to specific agents who are just responsive to the actions and processes of others. What are the update rules? So these are the decision rules and the chance processes that agents, or what I'm calling might have. What information is available when they make this decision, or what information is available when the system updates through these decisions? How do they use this information, and in what order are these decisions or updates made? So this connects back to the GDS framework that we've also discussed, that the state variables being tracked and the update rules, what information is available and how is this information used, connects us to inputs and admissible inputs. And state update rules are a part of, I see. I've been told my signal is breaking up, so I'm going to kill the video. Can y'all hear me okay?
Yeah, it's okay. It's broken up a little, but yeah, you're good now, I think.
Cool. Hopefully some of what I said so far came through.
Yeah, I think most of it was intelligible. It's just it was choppy.
Good. Okay. Well, we will continue. It's actually funny because we just said what information is available, and we just had an example where some of the desired information wasn't available. And parameters sometimes may not always be separable from the notion of update rules, but a parameter is something that is set outside of the agent choices. Kind of often think of it as outside the initial system's operation. The famous example that I've always heard is when you set the steering wheel before you put the car in drive, that is a parameter, the angle of the wheel in relation to you. And then the angle at which you turn the wheel to move is a variable. The parameter influences the system, but it's typically not changed during system operation.
It looks like we just lost Octopus for a moment. Maybe they're reconnecting. I'm going to make a comment while Bertha's in the chat while we're waiting. So we're doing this work on knowledge organization infrastructure within block science, and if you think about it in the context of what Octopus was just saying about what information is available and how can it be used, for an engineering firm, a lot of our relevant information is quote knowledge or knowledge objects, and that work is a lot about practically figuring out how to capture, organize, and access knowledge objects in a way that can be both produced and consumed in a distributed way, which also puts a lot of burden on how things are organized so that you can discover relevant things and or translate across different ontologies or domain areas. And so just figured it would be an interesting observation that a lot of that work at the org level is actually addressing this question that is under update rules here. He's back, so I was just kind of filling time.
I appreciate it. And it sounds like there was something relevant there. So I'm really glad we're on adding value so far. And I would add one more framework of modeling, which is this is meta modeling, but communication strategies. So if we have incredible results, but the client or the audience doesn't find them comprehensible, we won't have the impact that we're looking for. And MAIDs seem to me to be a very good communication strategy. But in general, communication strategies are part of the model. So to wrap up the review of what we've discussed with MAIDs, there was a lot of value in the things that they could do qualitatively from the graph structure in terms of communicating structure and dependencies of information flow. Specifically, there are information relationships that can be determined algorithmically. Things like directional separation, strategic relevance, and how different variables depend on each other in different causal inference strategies, etc. It was also nice that they connected to Bayesian networks. Bayesian networks could be viewed as either a very specific class of MAID, or MAIDs could be viewed as a enhanced version of Bayesian networks, but there's a lot of relevant literature there that I was happy to see some of for the first time. And then there were also more precise quantitative things that we could do when we threw in numbers. Like we could associate to a strategy a notion of expected value based on the numerical values that we associated to different outcomes for different agents. And there was also an algorithm for finding some of the Nash equilibria of these multi-stage games once we have these expected values. So they're powerful tools in terms of what they enable, both conceptually and technically. And that's what we've covered previously. And what we want to now present is some commonalities between MAIDs, GDSs, and CAD CAD models, and most specifically, some CAD CAD modeling ideas that I've been developing that were really inspired by MAIDs. And you'll see how once we get into them. So I'm going to review here what a CAD CAD model consists of. This was a little compressed when we did it last time, and I'm not assuming any prior knowledge. So there are 5 parts to the CAD CAD model as we're defining it here. Some of these things like, okay, this is a dictionary. Well, maybe that's not true of all CAD CAD representations. I'm talking specifically about a particular Python representation. But we have a state, which tells us the variables that will be updated, the parameters, which are the external information about the system that's set prior to the system beginning operation or the simulation beginning computing. With policy functions, which are used to turn current state and parameter information into information that can then be used to actually update the state through state update functions. And these policy functions and state update functions are combined into partial state update blocks, which tell us how states are updated, in which order, and which policies are used in updating those states. So one thing that creating a MAID tells us is something about what a CAD CAD model structure might look like. For instance, if we try to translate the MAID directly, we know right away what the information dependencies are between the variables, what variables there are, what information is available in making the decision, etc. And I think it's fairly reasonable to view. So structurally, the MAID has these different levels of dependencies in terms of the stages of the game and the order in which things happen. And one reasonable thing to do is to look at those stages as a potential way of corresponding to the partial state update blocks, so that when we're building these models, the partial state update blocks correspond naturally to the stages that have been identified. Certainly, a later partial state update block would be depending on earlier information. And this makes that information dependency very explicit via the arrows that show either direct influence or information availability, or in other terminology that we've used from GDSs, controllability through the solid arrows and observability through the dashed arrows. So in this instance, you can translate the stages to partial state update blocks very directly, giving labels as to what is happening. And also knowing here what information would be needed to update specific variables that we would want to track. I would take an aside here to say that this translation step, I don't believe requires any deep coding knowledge or experience. I think an intelligent non-coder could do it. I also think that potentially an AI model could be trained to do it. And I believe that there are people who may be working on things where you can directly create structures visually that then translate to something like this. The important thing is the two structures are in parallel and each gives information about the other that may be potentially helpful in the modeling process. By the way, we don't have 79 slides, don't worry. So in building these stages, these partial state update blocks that correspond to stages of the model, we have the policy function that do the internal logic of processing information for the most part. And then we have the state update variables that handle actually changing the values of specific states. And there are reasons that I won't go into at this moment why it is useful to separate those. Policy functions are doing this information processing, and one way we could look at them is at the level of GDS. They are determining an input from the space of admissible inputs, or selecting the input to the state update. Several state variables can be updated at once, which could represent simultaneous independent events. And in the model that we have here, where both the tree dying and the patio being built are simultaneous decisions, it makes sense to put them in the same state update block here. In the partial state update block, there are two state update functions. These numbers, there's really no required relationship between the numbers of policy functions and the number of state update functions. It's structurally that these policy functions feed information to the state update variables through an internal mechanism. And one thing I hit upon, I think that it would be useful to me, at least in the future, is that if we're using this in terms of agents and decisions, you can create a template for what a policy function looks like if that policy function represents a single agent decision. So step one is looking at the available information. And the available information here, if we capture it early, can be tracked through looking at local variables, which will be just tracking what the inputs are currently. After that information is captured, I have a code block here, and all it does is define the agent name and the decision that is being made. And finally, that is passed to a decision rule. Decision agents in this framework are going to live in the parameters of the CAD CAD model. So what we're doing here is accessing a particular agent from the available parameters. And then we're asking for their strategy, which contains rules. We're getting the name of the decision that that agent needs to make, and finding the rule logic that will be applied. This stores a function that has been pre-allocated somewhere. And this decision rule, once it's been created by summoning it from the information in the parameters, can then be applied. We can plug in this available information to get the decision and pass that information along. So all of the work that needs to be done is outsourced to an agent that lives somewhere else. And in a moment, we can talk about how that agent is created and where it lives. But what I like about this, in thinking about my former students who were non-coders, is they can do the modeling step here independent of the coding step, and they can do it in parallel for greater efficiency. So all they would have to do to implement this, and something that might be useful in general with modeling teams to separate modeling and coding, is one person could have the task of naming the decisions that need to be made and just changing this piece of information. This could even be something that AI might be able to do from a verbal description that's copy pasted that in like a document, and then they identify, okay, these policy functions correspond to agent decisions. This agent is making this decision, and that's all the information that needs to be added to complete that structural part of the model. Then the coder will have to do the work so that this actually works. They'll need to be creating agents with strategies and rules that can make this computable. But it's sort of a separation between front end and back end, where the domain modeling and the back end is the coding, and by separating them, we remove some dependencies and make them parallelizable. In order for this to work, the decision rule step has to work. In other words, this actually has to do something. And so this is where the coding structure of creating agents comes in. Now, there are many different approaches one can do computations through agents. And it's, a massive amount of computational and engineering literature about it. I'm going to show a framework that I felt worked for me that may be valuable. We're going to give the agent structure in CAD CAD exactly what a MAIDs agent would have. So they need to have a strategy, and they need to have a total utility. The strategy consists of decision rules that look at the current situation and make some decision that needs to be made about changing the value of a variable. The overall utility consists of component utility functions that assign values to specific outcomes and then combine them to create some notion of overall utility. So the coding framework or structure that I'm playing with here just makes these things explicit and says there needs to be spots in the code for anything that a MAIDs agent has. So MAIDs agents have decision rules, and so there's a decision rule class. That means we have to define what the decision rules are for the agent. I like to have things have names. It's not required, but I would want my decision rules to have names so that I can tell them apart later after my experiments are over. Another thing that would be helpful, or that's necessary actually for the MAIDs framework, is to be able to build individual utility functions that they can be named as specific approaches, and these should take the current state of the system and map it to a number in some way. So both of these are things that exist in the MAIDs framework, and we're just putting them in code so that we can utilize them in CAD CAD models or other types of simulations. Then decision rules can be combined into strategies. And one of the big technical things that MAIDs enabled last time was that we could look at the expected value of a strategy. But the notion of a strategy is its own entity that can be implemented in code. And so we have names of strategies here. And then we have a space where we can plug in what the rules would need to be. In a moment, we'll see a specific example of this where we're looking at specific agents from our specific example, and it may become more concrete. I vacillated a bit on the terminology here. I believe that in Sean McCohen's work on MCML, you have something called utility options. And go ahead.
Oh, I was just gonna comment. Yeah, so I actually have basically similar to this a bit like for a boundary action and a policy and let's say control action. Those are like the abstract classings of them, and then you can have like let's say policy options where you implement, either zero if you want it to just be like a very vague scaffold. You could implement one if you just know exactly what you're gonna do, or you could have multiple if you're gonna do things like A/B testing, or you want to compare different potential options that satisfy that broader abstract class, but have different kind of like logical implementations. So yeah, you're exactly right. Yeah, sorry, I just wanted to add that little tidbit in. Thought that was a good point.
Well, I appreciate that. I think the implementations are likely compatible, and I'm certainly not trying to reinvent the wheel with things you've already done, but I think that they're compatible in terms of translating between them, and maybe this is just a framework that can translate to yours as well.
Yeah, so I actually have I had put after the first session into the backlog to some point at some point come back and
Ah,
actually
cool.
this the backlog's just huge, so I haven't it's not near the top yet, but you get what I mean. Like I have a note to myself because I actually really would love to if I can get some time to come back to this and see, how compatible the two frameworks are. And I don't want to take up your time, but you get what I'm saying. Like I'd
Oh
be
yeah,
very
I totally do. And I'm not I'm also not claiming any great intellectual innovation here. A lot of this stuff is basically just based on things that I've seen in different types of agent-based modeling literature translated to a specific object-oriented representation, and then filtered through this additional information of what a MAID structure looks like. There's lots of agent representations that work well. I love them all, though. I love agentic frameworks. So I'm happy to get a chance to discuss one. Final piece here is the agent itself, which should probably have a name. Now that I'm looking at it, that would be useful information, but is a combination of the strategies and utilities that, again, all of this is being translated from the MAIDs framework so that we can translate some of those ideas. So what this creates a need for is more indirection, which there's this saying in computer science, there's no problem you can't solve with enough indirection, except having too much indirection. And we need specific decision rules that will be for specific agents. Now, we are currently high-level agnostic as to what the actual decision rules are. What we're doing right at this moment is just a mechanical diagram that says there needs to be an engine here. And we're not saying whether it's a diesel engine or a gasoline engine, but we're saying there's an agent who will need to make decisions about whether or not to poison a tree. There's an agent who will need to make decisions about whether or not to build a deck. It's possible that you could get away with not doing this level of inheritance. I like it, but if it turns out to be more efficient another way, I'm not advocating for it. But same thing with the utilities. There's this level of indirection where you subclass two specific value functions. And then when we actually want a specific agent, we have to say what the specific poison tree decision rule is. But before we do that, we look at what we're going to do with strategies. So here's what a specific abstract strategy looks like. This is an Alice strategy. Alice needs to have a rule for poisoning the tree and a rule for building the deck. And I've implemented those as dictionaries. Again, different approaches would be valid. The important thing is what is needed here is the decision rules. And those are things that we can plug in for specific decision rules. Similarly, if we have individual utility functions, we can access those and keep track of them with the ability to combine them in ways that we want. So it might be useful to add here a total utility that combines these in some way. But regardless of whether we calculate it, we have the information that would be needed if we know how the agent values different types of information that come to it. And then an Alice agent is just an Alice strategy and an Alice utility profile. So this is a little bit backwards in terms of how you might think about it. Top down, we probably think of the Alice agent first, and then the strategy and the utility, and then the individual rules and functions. But from a logic perspective, we have to define these things. Otherwise, we'll get dependency errors. And so it builds up from the bottom up. And then what does this enable us to do? So there's always a trade-off when we do objects. Some people love object-oriented programming, some people hate it. I personally love it. The one thing I could count on for my students was that they had been through Intro to Computer Science and they could write a class in Python. So that was often my starting point anyway. I'm biased in that direction. But there are lots of problems, if you think about it, where agents and decisions are naturally the right entry point anyway. That's a well-established framework in economics. For a lot of blockchain problems, there are specific roles, and it might make sense, at least at the beginning, to think about the different roles belonging to distinct agents who are making decisions. Another thing is that this is often very natural. So the question of who is doing what, I believe that you could type this out in kind of a quasi boilerplate code, even if you're not positioned to build the individual decision rules and value functions. So there's sort of like a very cursory knowledge of coding that's needed here that, again, could be something that is a process that people learn where you can decide which decision rules are needed and name them and work in parallel with someone who is actually building the decision rules logic. And that relates to this notion that I often encountered in my previous research work, which was about handoffs of I don't have one or two really smart people, or I have a few really smart people, but they're all beginners. I don't have one or two experts that I'm collaborating with. I have 3 to 5 people, each of whom have some skills and are developing others. And so the ability to work in parallel and to do things like, okay, you're going to write this mock code, and then we'll come back later to more specific code was really valuable in terms of making progress. For the level, again, of the ability of a block science member is much higher than the teams that I was talking about, but the notion of handoffs is still going to occur, and having a template may be helpful. The other thing that I love problems that explore rule spaces, whether it's in cellular automata or genetic algorithms or finite state automata. I've always been attracted to problems where you're searching for a rule that does or does not do something. And by structuring the code in this way, what I'm trying to do is to make the rules a point of emphasis, that you can't proceed unless you are clearly defining what rules you will later fill in. I've found that if we need to iterate on something, so we know that part of the process may change, then we can build the model in such a way that that part is easy to change later. And that's what this is intended to do. If we want to try a different decision rule for poisoning the tree, that is built in, that we're going to be able to drop that into this box without needing to decide on what the right decision rule is. And if someone changes their mind about what the right decision rule is, it's much easier to write it at this stage. It's much easier to rewrite a small part than it is to come in and make a fundamental change. So we're creating places where we can drop in changes easily for experimentation and iteration. This makes it easier to search for adaptive and adversarial strategies, especially in situations where it may be difficult to work with some of the formal techniques for finding Nash equilibria. If we just generate a bunch of different strategies and see what happens, this is a way of doing that easily, which can be an alternative way, kind of a bottom-up way to get to the same place that we might work with backward induction. But this requires less, analysis and puts more on our ability to creatively code and just say, okay, we can. It's kind of like a Wolfram new kind of science approach where you say, I know lots and lots of rules and I can see what happens with those rules more easily perhaps than I can set up an analytic framework to solve for something. I'm going to take a short break here to see if there are any questions or thoughts before I move more specifically into what rules look like in this framework and how you can combine different rules to search, different model spaces.
No, I think that I've been looking forward to the next part and see how everything comes together. Just in terms of CAD CAD though, maybe a question. So who are supposed to be the agents in CAD CAD? And what type of equilibria would you be finding?
Okay, yeah. So the agents are going to be dependent on the situation being modeled, and that's why we're being as general and agnostic as possible. But I would advocate, or my preference in terms of design, maybe I don't advocate for it, but maybe my preference in terms of design is that anything that has the ability to, anything whose state variables need to be tracked, or anything that has the ability to make a decision that can change another agent state variable becomes an agent. And this would include a natural process being viewed as a passive agent.
So basically, it could be a function, is what you're saying, like a policy update function or something like that. That could be an agent.
A policy update is not an agent. A policy update is a decision made by an agent in this setup.
So if you go back maybe a little bit back to where you define, the elements in CAD CAD, you had, parameters, you had inputs, so just to understand from that structure, what could be an agent?
Yeah, so an agent is defined outside of the model itself. And that's, I think, the agent doesn't actually live in CAD CAD. The agent is an external thing that CAD CAD is going to call in a specific way for policy and state updates.
Yeah, I
And
think it's worth noting that like CAD CAD's job isn't to build agent-based models, it's to kind of orchestrate them to sort of like build out the world. Another way to think about this is as the kind of opposite of a reinforcement learning environment where like people go and build benchmarks for RL and then try to like look at how their agents behave, but you mostly use the benchmarks to develop that. CAD CAD is like less caring about the structure of the agents and more caring about the structure of the world of the game. So you're building a model of how the world works. And then to Octopus's point, you're just assigning an agent a certain amount of decision authority. You're like, hey, you functional block who we are imputing the idea of agency onto. We're saying, hey, this is an actor who's going to take decisions based on information and possible goals. But actually, all we've done is said, here's some information that's available to a decision-making process. Here's a set of decisions that you can take. And then there's a world model that determines the consequences of that, or broadly orchestrates many actors who have different observable and controllable spaces to see the consequences of their interplay. But these don't have to be agents, strictly speaking. Some of them might be agents, some of them might be populations, some of them might even be algorithms that we've designed and that we're saying they're decision-making policies that we're testing. So I think it's important to focus on CAD CAD more as the world modeling, the tool for structuring out the world model, less than the agents themselves. We should be able to put any agent in any decision-making context in CAD CAD as long as they have appropriate domains and codomains, as long as they're, forming beliefs from information available to them and rendering decisions on their output spaces. Like we want to be agnostic actually up until we build a specific model.
Oh, I see. Okay, but then based on that example, a block could be an agent, right? Like.
Yeah.
Okay.
And I think, but also multiple blocks. So one thing that this it's interesting, right? A couple different things could happen. We could have a model like in the MAIDs where there's an agent who has multiple blocks associated with their agency in the sense that they are making decisions at multiple stages in the game. They have different information at different availability. In that example, you could think of it kind of like a board game where you like there are stages in the game, and during a particular stage you have a turn, and during that turn in that stage you get to do certain things, and then the game state updates, and maybe you have a turn in the next stage where you have different choices and different information, but different players are playing, so they're gonna all have to do their turn during the stage in a very specific way, but the agent is actually outside of that framework by one level, and they're making decisions again when it's their turn. Does that make sense? So
Yeah,
they're not
definitely.
in the block.
I think that actually helps, that sequential thought. Okay, I see what you mean.
Yeah.
All right.
The whole MAIDs way of interpreting a CAD CAD model it's probably best to think of it like you're playing. I mean, they're repeated stage games, but you can literally think of it like you're playing a board game. Each stage in the stage game is a sort of round or like again like a phase of a game, and then like the players are going to act often in parallel in the CAD CAD models, so they don't know what the other players are doing, but they get the information. Everyone can see some aspects of the state of the game, and then there might be some private information, but then you make choices and the board game iterates, and then you go to the next stage or the next phase of the game, and so you increment through a whole round once you've played all the phases, and the game recurses back to the beginning, the first phase again, and you play through. And so when you think about CAD CAD models like board games, it does a couple things for you. One is it helps you kind of factor apart like what makes sense to put at the same time and what to make in sequence. And it also helps you think about which actors should and shouldn't know. So you can imagine things like having a handful of cards that only you know versus having game state on the board that everyone can see. It also helps you think about how you structure the state space. So one analogy to board games is that when you make a board game, you need to think about how complex the piece set and the board is actually. That's close to your state space model. You're like, oh, well, like what is the actual physical stuff I need to implement this board game? That's the stuff that is going to show up in your state space model, like your model of the world. And then your rules are encoded in all of these, policy functions and state update rules and such. They're like, when you do this, this happens. How does the game state change? And in the board game design setting, all the computation happens in people's heads. So it forces you to learn the rules, but also not overcomplicate the rules. So like good models have very similar attributes to good board games in that they only have as much complexity in the state space as they need. They only have as much complexity in the rule set as they need. And that there's a variety of different kinds of decision circumstances that the players are faced with, often with incomplete information and often with chance mechanics like dice rolls. And so, I mean, this might just be a fun exercise for the future to do a kind of like CAD CAD model board game design exercise where we just level up people's comfort and skills with the tool by trying to, design a board game. Anyway, I'll stop talking now, but like for anybody who's interested in learning more about this, this might be a fun exercise.
Okay, great. Yeah, that's a good idea. Thank you. Thank you.
So, Octopus?
Yes.
All right, so depending on how this communication model is deployed, during simulation, a CAD CAD simulation, the internal state of the agent is observable. Okay. If this communication model, if this was deployed, the internal state isn't necessarily observable of the agents themselves.
That's true. In Java, you can actually make it invisible. In Python, you can't. But you don't get anything out of the players cheating because the purpose of playing the game is not for agents to win. So where that comes up is when the decision rule is created, whoever the modeler is has to create the decision rule in such a way that it only accesses relevant information. And if somebody wants to cheat and break the model by looking inside and saying, oh, Alice shouldn't know what Bob's strategy is, but Bob's strategy is actually public information that Alice could look at. If you create an Alice who does that to quote unquote win, it hasn't helped the modeling process. So from a technical computer science level, what you're saying is accurate. It's just on the user to use the tools in such a way that they don't create nonsense, which is important to be careful about because like in machine learning, you often have these feature variables that are not actually available when you make the prediction. It's kind of the same, data leakage problem that you're talking about here. But that's how you get around it is when you're modeling, you're careful about that. And in particular, when you create a specific decision rule. So here is an example of a specific decision rule. The constant ones are not so interesting. You can always do true or always do false. Although those can be really helpful in terms of kind of setting the boundaries of the strategy space, just like you can approximate arbitrary functions with piecewise constant. Well, you can't approximate arbitrary strategies with constant strategies, but you can start there, sort of a cognitive approximation. But here is an example of a decision rule where Alice only builds the deck if the doctor was called. And so what's happening here is we're taking the previous state of this basically the way we've set this up is that policy functions always punt to agents. And so whatever the agent gets is whatever the policy function got as input. And so I can just say X, knowing that that's going to be the dictionary of, the dictionary of arguments that were passed into the policy function. If I decide to cheat and say get previous state or get params, get Bob's strategy, I can do that, but it's not going to be accurate. And so it's on me to make sure that the level of information availability that's used in the function and message passing is accurate and that I don't distort. In other words, we're only hurting ourselves if we break that invisible accessibility barrier.
I'm sorry I didn't cut you off because I was learning from what you said. But what I meant was, okay, this type of agent-based modeling, right? CAD CAD is used to design, from my understanding, network policies. I was giving an example of a communication model being deployed as a probe over a network.
Oh,
Cheating.
okay.
Like, so it's like somebody can design a communication model that is essentially a probe that can be deployed on a network. Right?
Right.
So the cheating thing, I mean, that's not necessarily useful from a network policy design perspective per se, but like the whole purpose of it is that the structure of the network doesn't create some whack-a-mole situation, right? You want to, so it's supposed to approach Nash equilibrium, but like when this is deployed, right? When this is deployed, it's a scenario in which the internal state of the agent is discussed by maintainers of the network. Okay. There could be like reports between network updates.
I see what you're saying. It's like a
In other words, the internal state and of the agent itself is kind of a vulnerability in network deployment because they will be used. I mean, I shouldn't say will, but I mean that's how I'll be using them.
yeah,
I would use them as probes. I would take this communication model, design some kind of organization with games, and deploy it as a probe. Is this happening? What's observable? Because these agents could be deployed to have real world input. The communication model itself. Like, okay, remember I like during the first presentation, there wasn't enough information about the agent, so I freaked out. Because I wrote CAD CAD, so I was thinking of state policies. I never really I only attributed policies to behavior. Right?
Right.
So the only thing I could go up to really was strategy. The personification of of agency itself kind of freaked me out a little bit because it seemed like it was limiting but for the purposes of storytelling. I understand why you're using like personas for this because it enables people to understand it and introduces them to the topic. That's why I went straight to system identification because I perceived it as some sort of like vulnerability, but it isn't. It's an education. It's a means of educating people about it. So my apologies.
No need to apologize. I'm glad my answer was somewhat helpful, even if to the wrong question. I would say though that agent modeling is a philosophy, like in the most extreme, everything is an agent. Like there are, gas models where the particles are agents. Even though we know particles don't make decisions, or maybe it's not useful to think of particles as making decisions, you still give them extremely simple strategies. And then if water is flooding the Grand Canyon, there was a famous agent-based model where it was Santa Fe Institute, Summer Institute model many, many years ago, where water was flooding the Grand Canyon and there was one agent, which was the water. And so even you can assign an agent designation to things that aren't very actually agentic. And that's the naming and the specific people can be helpful, but this framework can be kind of fit to anything. You can view the gears in a machine as agents. They just have very limited decision making and have to follow specific rules.
I think the key here is that we're talking about the way in which basically space and time are related, as ridiculous as this sounds. You have a set of states of the world, and then you have a set of rules by which the next state of the world are rendered. And we choose to kind of overlay this idea of agency when we're modeling humans or human-like systems or anything that has, let's call it discretion or judgment within its purview. But I think, one of the reasons why we've been developing out GDS is to try to provide a clarity on this like abstract pattern, which is to say you have a state of the world, X. So this is just how things are. And then you maybe have, let's just for the moment assume that that state is fully observable. It doesn't have to be, but let's say an agent who can observe that state in its entirety, it then has a set of things that can do. If that set is a singleton, you have a system with no degrees of freedom, right? Literally none. If you're talking about the gear example, or probably the water fits this, though maybe a little fuzzier if we have some uncertainty or some stochasticity, at least in our model. But ultimately, let's say that it's deterministic. That means there's a singleton, your set is a point, and you get a discrete dynamical system literally. Given the prior state, given the decision rule, given the way in which the laws of motion work, next state is deterministic. Just by saying, hey, wait, that's not always a single point set. Maybe there's a collection of points. Well, you get a discrete differential inclusion if you don't include the selection rule. You get something that feels like agency in a meaningful way when you introduce the idea that we don't actually know or can't pre-prescribe the choice function from the set. We know the set, we know what happens when you pick a point from the set, but someone might have some private information or some internal goals or something that renders their choice not totally known or understandable a priori. Does that make sense? I actually kind of want Jamshid to jump in here too, if you don't mind.
No, I think that's right. I mean, what we're trying to do really if we look at it purely from a GDS point of view, is to separate out the things that individuals themselves, when confronted with the world as it is, they have a menu or let's say a plethora of opportunities if it isn't a singleton. But we always want to admit the possibility that there are external influences that can change that type of universe or that landscape that they can choose from, and that can occur irrespective of what you would like to do, in a sense. And so we want to be able to map the admissible action space to things that can be realized by the system over time. And that kind of gets back to the notion of whether or not the system can actually realize certain states. So we get to that reachability criteria as impacting whether or not individuals themselves are going to find themselves in a position where their admissible action set gives them the opportunity to choose a thing that they might consider to have perhaps a measurement or a metric of saying what they consider to be the best. So I don't know if that further clarifies or less clarifies, but it gives at least that idea, that spread of what happens when you move from a singleton into something which is dependent upon things that are outside of your control.
And I think I'm trying to emphasize that this notion of agent or agency or decision, discretion, the ability to make a choice. So as we move along this continuum of, think of it like the cardinality of the admissible action space, going all the way from literally you don't actually have a choice, it's a singleton, to a high dimensional or potentially highly sensitive collection of choices where the choice that you make has large ramifications on what happens in the future. That gives us a way of identifying this, again, moving from on one extreme, this thing where we're modeling the gear or the water, or the particle, which has a questionable level of agency, in a large part because the decision rule itself is pretty fixed. It's we don't see variation in it. We could think of it more as a law of motion and less as a choice from a set. The moment that set becomes non-trivially diverse and that the downstream effects are sensitive to it, we start to see something that looks and feels like agency or discretion. And that thing itself can expand from something extremely narrow to something extremely open-ended. And that if we I guess I'm kind of trying to trace a line along this dimension of not just how large your set is, but how sensitive the system is to your choices. Because you could also have a big set, but for which the consequences of your choice don't affect anything that matters to you. And so I think especially when it comes to designing these systems, we're dealing with agency potentially of individuals, potentially of organizations, potentially of anything that has to make a decision rule or take a choice from a set with some intended outcomes. It can be really important to understand both what they can observe in order to make an inference or a choice, and then what their choices actually are, and then how those choices actually ultimately do or don't have effect on the trajectory of the system. And so, we've really pulled out with GDS this idea of this set. That was probably the most substantive contribution of that work, and ongoing, is to like make explicit the idea, hey, there's a choice here. Like, is it non-trivial choice? Under what circumstances is it a non-trivial choice? How much does it matter what the decision rules are? And, and that kind of thing. I don't know, that's kind of a long tangent, but I'm hoping that it's helpful for tying this discussion back to the GDS part.
This is in computer science and physics. I think this is related to the notion of daemons, where you have a natural process, which then you switch the perspective and say, this is under the control of some agent that may be making decisions.
Yeah, you're right.
There are some components to finish up the framework. Yes.
Yeah, thank you so much. Yeah, actually, just wanted to leave you with, I don't know if you're gonna for this part, but basically the question I have is, Nash equilibrium with this approach, but we can talk about that when you're done with your slides, okay?
Yeah, sure. So some other types of decision rules, probabilistic. We already talked about this one, but here's one where we only build the deck if the doctor was called. And so that makes it clear that we're processing some type of information. I'm going to follow what you said and call this world instead of X. It's much clearer. So then we combine different rules into different strategies. Here I have 4 different strategies that could be applied to Alice. The nice one, where we never do anything. The mean one, where we just are as aggressive as possible and always poison the tree and build the deck. The random one, and then the one where we poison the tree, but we wait to see if the doctor was called, because we don't want to invest the money to build the deck if we don't think the tree got sick. So after we would combine the rules into strategies, then finally pass the strategies to different types of agents who will have different utility profiles, potentially, and different strategies to assign. And then where you finally go is you can set different types of agents as parameters to sweep, or even different populations of agents, depending on what you want to do. And once the agents are now inputs to the model, this is where things open up, because what you can search for is how the output of the model, whether that's defined as a single number for like viewed as some type of metric, overall metric, whether it's some set of performance guarantees, of constraints, of satisficeability rather than optimization. Once you have a way to turn agents into simulations, then you have the entire set of search and optimization strategies over the space of agents. And that's really what I was wanting to get to, is that this is a way of using CAD CAD's adaptability and flexibility to still do something that is entirely an agent-based ontology of everything factors through agents, but then those agents are playing on the grid, on the field of CAD CAD, and then we can use the fact that CAD CAD is a well-structured and performance simulation engine to test what different strategies and different combinations look like. And I just prefer to do that through something that makes the components of the agents very modular and explicit. So that's the overall view of this. Is why would you want to do this is so you can test what happens if I bump this agent, what happens if I introduce these new agents, and you can do it in a way where the CAD CAD model is set up at the outset so that those types of experiments are iterated quickly once you've done the effort of setting up the structure so that the agents are a primitive.
You could describe the experiments more efficiently so it's also faster to construct them. I think we spend a lot of time trying to design experiments, and not that that is totally automatable, because it's not. You need to be able to reason about what scientific questions you're asking and how you're going to answer them. But the more templated or standardized the meta framework is, or the easier it will be to map intuition of an experiment or a question you want to ask to a simulation that will help answer it.
So that's what I have prepared. Oh, I'm sorry, I do have one more thing here, which is that this is kind of the philosophical question we were looking at of passive agents. So in this framework, everything is an agent, even if it's not something that you would traditionally think of as having agency. It's just that you don't have utility functions. It doesn't want anything. And it's ruled by probabilistic processes. So whatever the process is not dependent on the state of the world other than as potentially conditioning variables, but there's no, every rule needs to either be a constant rule or a probabilistic rule. You're not allowed to do that type of higher level processing. Like the tree can't check directly if Bob has called the doctor, but it does get that information as part of the state of the world. But that's the difference in terms of, and I like this because being able to flip from something being a passive agent to something being an active agent can be helpful if you're looking at like a system failure model. It's one thing if things fail independently. It's another if you're looking for the optimal condition under which the gears fail. And that can be viewed as I'm assigning a strategy of gear failure that's more active than just they fail, identically independently distributed. So being able to view everything as an agent means you can pass from different levels of information processing more easily because it was already an agent to start with.
If I was using this within the context, like within a software engineering context, I would take that was user driven. I would have one side be an activity diagram or something akin to that, and the other one be games. That would be an interesting. That would be interesting means of designing user experience. But that's it, right? Like this is a scenario in which this is a network.
Mm-hmm.
Well, this is not a network, but you understand what I'm saying. Like, given the background, like at this company, like designing network policy.
Yeah.
That's each. If you're relating these agents to daemons, they're actually daemons, considering the interface is a computer.
Quick question though, I think daemons in the sense of computers versus kind of demons in the sense of, I think the reference example is like Maxwell's demon. There's a couple other ones, but they're effectively, when you imagine an actor who can take a choice that is effectively a worst case choice. A lot of the reason why I see the use of the term demon emerging is that they're like their thought experiments or mathematical constructions where you realize like that something is a switch system or something's not under your control, and then you say, well, let's imagine that someone who's optimizing against me has control of that switch system, that choice, and this is sort of a proxy way of toy way of doing this kind of reachability analysis or worst case scenario studies, where in engineering we have slightly less abstracted versions of these, but they're the same in intuition, that if you know that you can't know how a choice is going to be made, then it's safe to say that the player playing that choice is your adversary or is someone who's trying to ruin your day, right? It's almost like a Murphy's Law type assumption. I don't know if you want to add anything, Octopus, but like that's my intuition from the mathematics and computer science introduction, physics as well, kind of demons. I see there as the equivalent of kind of engineering things where we're doing kind of worst case analysis. And again, the reachability study stuff is in that lineage.
I would, and I totally agree with you. And I would add to that, there's always that famous caveat / dunk. Don't confuse a random system. Don't confuse an adversarial system for a random one. But some systems truly are random. And if we view it as random, it's passive agent. And if we view it as adversarial, it's an active agent. And then this is just, I like viewing everything as an agent. That's my bias. So
Your
for
point about
exactly the reason you said.
Your point about the random versus adversary is a good one, but I think the key there from an engineering perspective is you're making a modeling choice, a judgment, a subjective choice about which is the appropriate representation for the question at hand. And I think there's some interesting circumstances where, maybe you have a system that is probably a random process and for which you might want to get expected outcomes or produce candidate trajectories using a random process model, but you might swap that very component out for a daemon, an adversary, in order to get a worst case solution. And the fact that you can do that both mathematically and computationally as inputs to your problem framing makes them actually mutually useful. It's actually understanding that they're useful for different things that I think takes the leap from the kind of more toy mathy computer sciencey publication-y world into the engineering world where actually a lot of the times we just know that we need to do both. One of them is going to tell us what we think might happen and the other is going to tell us worst case. And there's even some related tasks like trying to discover the most likely thing that is bad, which is where we do failure mode analysis. It falls right between. It's not an adversary, it's not a random process, but it's of the things that are probable, which of those will cause it to fail so that you can mitigate risks.
Yeah, well, we have 5 more minutes. I'm happy. I do have to have a hard stop at noon, but happy to come back to Carolina's question of how you would search for Nash equilibria. What I could think of is something like it depends on how much structure the strategies have. But I think the strategy for a large scale search where you can't utilize some type of well-known optimization procedure would just be to bump, like do something like hill climbing where you make a perturbation to the existing strategy profile, see if it changes anyone for the benefit, make a small change. And that's one reason that I like the granularity of these decision rules is it lets you make a bump in terms of the decision rule very easily by switching to maybe a different probability. I'm not super familiar with Nash equilibria searching techniques beyond what I prepared last time. So I think that because there is a little bit greater.
Yeah. Just to clarify, what we were looking at here would be a mixed strategy, right? Nash equilibrium.
It could be a pure strategy or a mixed strategy, but it would be about whether that was at the level of decision rules, whether they were pure responses or mixed responses in some way.
Yeah, pure Nash equilibrium does not necessarily exist, right? Not always. Where mixed strategy does exist, right? So I was thinking that maybe some agents have mixed strategies and some others have pure strategies, right? So how would you come to find equilibrium here?
I think we could construct it as a numerical optimization problem. Go ahead, Octopus.
Yeah, I was just going to say I would run tons of simulations that are directed in some way, generate and test with some type of strategy, whether that's with a derivative or not.
I think practically the most reproducible methodology here would be something where if you go to mixed, then you're going to you should be able to do if I can remember this correctly. Basically, since every run with a set of strategies can be thought of as like a sample, I think we should be able to, again, it's a kind of a model built with executing the model inside of it. So it's a kind of meta model thing. But this would be worth, I don't think I can rederive it in real time in 2 minutes. But just from a more general convex optimization standpoint, I think we should be able to construct a kind of loss function that's representative of the existence of a Nash equilibria. It won't be unique necessarily. So we'll have to have probably would have to step outside of the convex optimization framework into something more general nonlinear, but you would be effectively running a model or a batch of model runs in order to take an observation and then updating your strategies. I think maybe the best literature to go at for this might be coming back to some of the evolutionary and like learning models where we could imagine, I know this is sounds silly, but like a repeated game, where what you're saying is that the CAD CAD model represents the playing of the game. And then you have to have a kind of a resolution, or you have to run it long enough to assess the properties of the strategies. And then you would truncate that run once you got your fact that you needed. Basically, you could assess your loss function, and then you would bump up a level to updating the strategies according to some of the information you gleaned from the run, and then you would repeat until you could generate a fixed point. But that would require designing a loss function that was representative of being a Nash equilibria. But I think one thing that's interesting about this is, as I'm talking out loud, this might work with not just Nash equilibria. Like in a sense, Nash equilibria is a thing we could construct a loss function for, but I think we could construct definitions of loss functions that were characteristic of other equilibria concepts. So it might be an interesting place to explore, starting with Nash equilibria, because if we can do it for Nash equilibria, potentially we can do it for other, I think, more useful equilibria concepts, or maybe just more domain-specific equilibria concepts.
Okay, thank you.
In order for that to occur, there needs to be structure to what? Strategy? This loss function, would it require structure to the strategy of the agents?
I mean, what I'm basically saying right now, see, Octopus, thank you so much. What I'm saying right now is that when we have a simulation framework like this, a tool like this that allows us to run, quote unquote, an experiment where we choose a bunch of strategies and run to see what happens, but the strategies themselves, they're functions, and we could say update those functions based on the outcome of a run. So now we're getting into like learning rules and like second order systems. So you run the system for a while, you update the strategies, and then you run the thing again. But there's a notion of a fixed point when the strategies wouldn't update anymore. And so that would be us solving something, discovering something. Just creating that set of procedures requires us to have enough of a model that we can define from it the loss function, and then we need an optimization procedure that minimizes that loss function. And ideally, we would want something where we have an intuition, if not a proof, that our procedure is going to converge to a fixed point, and that a fixed point is representative of some equilibria concept of interest. But it's an equilibria in the strategy choice, not an equilibrium in the behavior of the system. Might still do weird and interesting stuff, but none of the agents have an incentive to change their strategy.
That's cool. None of the players.
Yeah, I just think that it'd be great to kind of, define what conditions would guarantee that we'll find such equilibrium. If it exists, I'm just concerned whether there could be cases where it doesn't, or it will depend on how we define it too. So
I think there's an idea, this is sort of meta, but basically we have a piece of machinery that can execute a dynamic game, and within that dynamic game, let's just imagine that there are agents that have observable and controllable variables. Keep it as simple down to like just sets, right? I have a set of things I can observe, a set of things that I can act, and a function that chooses from my observations to my actions is my entire description of my strategy. It could be that it's a very complex set of functions at different points of intervention in a complex game, but for simplicity, we just smash it all the way down to I have a set of observables and a set of controllables, and my strategy is a function that maps the history of my observations of my observables to my choice. And again, this is the way that you would smash like every reinforcement learning benchmark problem. It's like the job is to make a thing that takes what it sees and chooses what it does potentially to optimize its own objectives. But once you have a game with, let's say, 2 agents or 2 or more agents playing, then you can view their function as their policy, as their strategy. And then the question becomes, if we know, say that they have utility functions or they have some revision rule, which is where the kind of Nash equilibria stuff comes in. It doesn't necessarily have to be unilateral best response. It just has to be a revision rule. As long as they have a revision rule, now we have a sort of higher order dynamical system. We can say, play the game, and then after a certain period of time, you get to stop, revise your strategy, and we play again. And as long as you have that construction, it should be possible to find some assumptions under which this has existence, uniqueness of equilibria, and convergence, and potentially convergence properties of a procedure. But the tricky thing about this is that we'll end up with either really abstract kind of shape-like requirements where you say the following must be true in order for this to converge, or you have to do it for a specific problem. You're just like, oh, I'm working on this problem. What does this look like for me? And so that's the difference between like a canonical form and a specific application. And so if you're looking at control theory or convex optimization, you see lots of results on canonical forms for a reason, because they're statements about anything that can be cast like. And so, and this is true not just for convex optimization, for other forms of nonlinear optimization. So I think your challenge here is that most likely you would do specific versions of this for specific problems until a pattern emerged, and then you might draw out a canonical form or try to make a statement in terms of a canonical form so that you can say, hey, for any problem, if you can make it look like this procedure is going to work.
Oh, I see your point. Okay, that makes sense. Yeah, exactly. Okay, so at the beginning, once this is deployed in CAD CAD, then it will definitely be problem specific, is what you're saying, until we come up with something that could be kind of generalized.
Yeah, but I think it's worth doing the specific projects where we're like, oh, hey, we have this circumstance where we're trying to analyze the optimality of a particular policy or something, and we do it from a constructed, hey, let's test the stability of these policies with regards to some revision rules by 1 or more agents. And then if we're doing that repeatedly, we might start to see enough pattern in this, or we might have the time or the interest to invest in trying to derive a canonical form that would help us say things about existence and uniqueness of equilibria and specific implementable procedures that will reusably produce, discover those equilibria. Now, they might not be unique for all, they might not, there's lots of things that we would run into in that abstracted canonical form realm, but I would argue that the GDS research is also intended to push in that direction. Like, we have these G functions in our GDS representations because in a multi-agent GDS model, you could think of this just in terms of each agent getting to revise their G function. And so we could ask questions in a almost more like a dynamic programming kind of way, where we're saying something like, hey, consider a 2-player dynamic game characterized by, G1 and G2, where, G1 is a function of Y1 and G2 is a function of Y2, where Y1 is what agent 1 knows or can observe, and Y2 is what agent 2 can observe. Then you have some sort of process that generates, X plus as a function of, let's say, U1 and U2. And so you take the current state X, which is hidden, you take the U1, you take the U2, you apply f of X comma U1 comma U2, you return X plus, then you retrieve Y1 and Y2 as observations to the 2 agents. They apply their strategy and they get, then they take their actions U1 and U2. So now we have a generic dynamic 2-player game. And what we don't know necessarily is, maybe it's hidden, but there's maybe there's a utility function or a loss function for each of the 2 agents that they're optimizing for. And so what you end up with in that setting is you can play the game and you can see what happens. And you can say, okay, well, after we've played the game for a while, we can let each player revise their strategies, or we can let them revise their strategies as they go. Those are two different dynamical systems, one which is batched out and one which is continuously learning. And so as you get those constructions, you can start to ask questions about the convergence properties of the different ways of attacking the problem. And it's actually, I think, non-trivial to compare what would happen in a model where you play the game, then stop, update your strategy, and play again, versus a game where you're actually learning, you're actually an RL agent, and you're just updating your strategy as you go, because that will require different ways of updating. And that generalizes to multiple agents, that generalizes to heterogeneous dynamics, because you have these more general input and output, domains and codomains for each of the agents. What can they observe and what can they do? And they don't necessarily know the whole state of the game. They don't necessarily know the rules of the game. In some cases, they can be affected by actors they don't even know exist. You can build whole networks of interaction effects where someone affects a state that affects the state that affects a state that is seen by an agent that affects a state. So like by the time their actions make it to you, it's completely unintelligible to you. You just know that the world moved in a certain way. And so you get a pretty big span of possible models, all the way from these simple two-player games, the canonical examples like the Pursuit Evasion ones, up to like complex network games with non-trivial interaction effects and heterogeneous laws of motion.
I see. Yeah, great. That'd be good to see. How far do you think that we are from kind of like having this first exercise in CAD CAD? Just to see, just kind of, get the full picture and kind of go through it step by step and kind of make sense of it.
Yeah, I would say that in terms of like examples, we just need this kind of thing to be scoped into projects in order for it to be like, my opinion is that we can do this now, but it takes time and effort because it's manual. Essentially, you have to design the experiment. The person who's done most work most closely related to this is Danilo, and it's never like a generic thing. It's like we're trying to answer a specific question. We're doing some sort of robust policy optimization through something like a PSUU exercise, but I think there are other kinds of questions that are more like equilibria questions that we can ask using similar methods. But yeah, it's bespoke. Like it has to be on a specific problem. In terms of doing more general stuff, I mean, the dimension on which we pushed on that is the research that Jamshid and I have done on GDS, which is more mathy, but he and I are both slammed most of the time. So we don't get a lot of progress on kind of writing up or testing out or building out proofs or anything. That's the kind of thing I'd like to see more of, but we haven't really been able to prioritize it because we just have, he and I at least have too many commitments. And I think as the org continues to grow and mature, I'm hoping to see more effort go into those things, but it's a slow, it's in some ways, it's the academic research part. And so it's always going to have to take a back seat to sustainability, but not like we don't want to do it, not that we shouldn't do it, just I work on it when I get the chance, he works on it when he gets the chance, and other folks, yourself included, are invited to push along those vectors with, space time or time that's underbooked, and I'm certainly happy to help. I'm actually kind of hopeful that some of the stuff that you're doing with the network games will push in that direction, because I'm particularly interested in phenomena where, I think we talked about this, where the agent's firsthand decision is actually about which links to maintain, but that their utility is derived from the process that runs over the graph. And I think that will create some of the circumstances where these kinds of analysis will be necessary to make sense of the games. Because if all I'm choosing is a link formation and preservation policy, but my utility is derived from a graph process, then my utility could be significantly affected by actors that I don't even know about, who are like 2, 3, 4 hop like neighbors whose, for some reason, their information is relevant to my utility, but I don't know they exist.
Exactly. Yeah, that makes sense. Okay, that's pretty interesting. Yeah. I think that next week I have my presentation finally. Actually, I apologize. Last week I was just a bit challenging for me, but I'm back. So yeah, we'll be discussing something like that next week at the EconPod. So
well, I'm glad you're feeling better.
Excuse me?
I'm glad that I was just expressing that I'm glad that the challenge is, you just said that last week was challenging, and I said I'm glad it's better.
Oh, thank you. Thank you so much. Yeah, no, suddenly you cut out and I couldn't hear what you said. Yeah,
Okay.
thank you so much. It's just that it was so awful. Like the first time that I would present and I got sick, I was like, oh my God, this is so bad. But anyways, so hopefully.
Totally okay. Looking forward to seeing the presentation, and I'm gonna go. Thanks for the chat.
Thank you, everyone. Bye-bye.